All right. Well, hello everyone and welcome to today's AVA. My name is Alex Alvarez, application engineer here at KETIV Technologies. Joining me today is a good friend and colleague, Philip Cox. Philip, how's it going today? You might be on mute.
There we go. It's going well, except, missing the mute button.
Awesome. Yeah, so Philip, if you guys aren't aware, he is a part of our design automation team. Again, design automation, pretty big piece of the pie that we do here at KETIV. So if you've ever had any questions, maybe you've reached out asking, how do you go about a specific process inside of Inventor or maybe Inventor API, chances are you might have spoken with Philip here. So again, this webinar is meant to be as interactive as possible. So if you guys have any questions, maybe something you didn't quite understand, please make sure that you do leave those in the dedicated chat box. So with that being said, I think we have quite a bit of information to cover. So I'm just going to go ahead and pass it over to you, Philip. Again, any questions, anything that you guys aren't really aware of, please let us know. At the end of the webinar, we do have a survey as well. So if there's a specific topic that maybe you wanna see or you don't find on our YouTube channel, just go ahead and let us know, and we'll make sure to accommodate as much as possible. So I think with that, Philip, go ahead and take it away.
Okay, thanks, Alex. So today, we'll go back up to, we're going to be talking about object-oriented programming. We had a AVA session last week. I think that we had some feedback from the viewers that they thought that it would be good to go through what object-oriented programming means and how we use it with Inventor in design automation. Now, a lot of times we hear it as kind of a buzzword, but it gets used wrong. So we're going to kind of go into that. Me real quick. Once again, I'm an application engineer at KETIV. I graduated from BYU and have worked for General Motors and Autodesk before. So we'll just skip on there. This is kind of part of a series that we're doing of going over the basics of getting started with the Inventor API. So if you've missed any of those and want to get started, here's kind of the first three of getting connected with Visual Studio, doing some basic geometry stuff, and then pushing values to your parameters. And we're going to use some of that stuff today in examples. But today is going to be a little more kind of theory and looking at code in our class objects. So let's talk about what we're going to do. First off, we will be talking a little bit about definitions. So kind of the theory of it, the difference between procedural programming and object-oriented programming. Then next, we're going to go into the anatomy of a class. We're going to do constructors, talk about what they do, properties, methods. Those are kind of the three basics that you kind of need to know to get started. And then we'll look at an example. It's not a fully fleshed out example, but I wanted to kind of have a sandbox that we can dig around in to give kind of examples and maybe get some feedback of what you guys would think to do to use object-oriented programming. And we're going to put that around a computer fan, as you can see here. So I'm going to go ahead and turn off my video as we're about to dive into the meat of this, and we'll go like that. Okay, so first let's start out kind of with what we're more used to probably, especially with iLogic and different things, and that is procedural programming. And this is where we have a project where we start with a set of variables, as you can see here up at the top, and then a bunch of functions. And one function calls another function, which might call two functions, which each might call a different function. And for simple, straightforward, logic, this works great. So, and this is kind of what was used a lot earlier. But as your logic begins to become more and more complex, it starts to get a little more wrapped around where you have functions calling, functions all over the place, and you're copying code, and it gets a little scary to the point where it turns into spaghetti code. So how do we avoid this? Well, how we avoid it is through object-oriented programming. So in object-oriented programming, it's based around kind of the 4 pillars that you see there on the slide: encapsulation, abstraction, inheritance, and polymorphism. And we're not going to go deep into all of these. There's plenty of content out there that you can go and look at for kind of the more holistic computer science view of object-oriented programming. What we are going to do is kind of focus in on an example case, and we're going to be making some widget. This widget's going to be a computer fan, and we're going to see how we would start to implement object-oriented programming with that example. So let's start kind of talking about encapsulation. So encapsulation means that we're grouping variables and methods into objects. What are objects? Well, an object is generally you're going to use a class object. So you can kind of see with the graphic down here that I've grouped things. We have this widget, which in our case is going to be a computer fan, and it has, in Inventor, we'd have the assembly, and then you have the 2 different parts. And so here we could use the parts for good excuses to make 2 classes. So we have the great class and the fan class. And so those would be classes, and when we made instances of them, they would be objects, so class objects. And inside that class, we have variables that pertain to that class. So like the great, you might have, the diameter of the wires that are going around it or whatnot, and then methods. So method might be to place it in Inventor or things like that. And we'll see that in the example. And same with the fan, they'd have different properties and different methods, different variables and functions that would work in there. And so what this does is it reduces the complexity and it increases usability, because you can have several different instances of the fan that you are just putting different variables into it, and you can call those same methods. The next is abstraction. So abstraction is about hiding complexity, and you hide complexity inside these objects. So with methods, a lot of times you pass in, you probably have all experienced it. You have a method that has 8 variables or something. Problem is when you go and change that method, then you have to go change where that method is called. Say you add another variable going into the function. You got to go change all that, and that might affect other things, and it just kind of cascades. So if you can reduce the amount of variables passing in and have that complexity inside the object, then it really will reduce the complexity and isolate the impact of changes. So that's another kind of pillar. Now, the next 2 we're not going to focus as much on because they're a little more advanced in implementing them. But inheritance, I like to think of it as a family of objects. So great and fan are both parts. What if we had a part object that held all the shared functions and properties of great and fan, so we didn't have to duplicate the code in between. So as you can see, the benefit, it eliminates redundant code. And then polymorphism, I like to think of it as you have many of these objects, and each of them have a function of the same name. So you have one function, but when it gets called in each of those different objects, say great or fan, so let's say we're calling the place function, it's going to have different results based on which class object is implementing it. So this helps you remove switch or if statements. I don't know if in your code you probably have very long switch statements or if else cases. So this helps reduce those and simplify your code. So with all of that, we're going to move on and talk about classes. So as you can see, when we talk about object-oriented programming, especially when we're getting started, we're talking a lot about how to use classes. And the first thing that we do with classes is we make a constructor. At least that's the first thing I do. A constructor is a special type of subroutine that you use to actually create an object of the class. So it prepares it for use. It accepts, you can put in arguments, variables, and generally you want it to get to a viable and stable status. Sometimes that's very simple, where you don't pass in anything to your constructor and you kind of have an empty class, and then you call additional functions on it after that. Other times you might want to pass in a lot of things to kind of initialize it. Here you can see an example where I think I pulled this off of our class for the fan base. We're passing in the box width and the box depth, and we just initialize some properties. So that's constructors. Okay. Next is properties. So properties, you might be saying, what is all these berries and fruits? I like to think of it as kind of the food storage of my class. So you're storing data, but you're also setting the accessibility of that data. So you don't want everyone able to grab, if you have, as I do, little kids, you're not going to put glass objects on the bottom shelf. And so in programming, you want to control where you can access certain data. And that kind of comes into private and public. So you can see here is some example code. We have a whole bunch of private variables. So box width, box depth, and the different instances of the custom classes that we're going to show. And here we, in the constructor, we've initialized these two variables. Well, we don't want anyone being able to change them outside this class without us knowing, just somewhere in the code. So we make them private, but we do want anyone to be able to access them and see what their value is anywhere. And so then we make a public property that they can go grab that value. So this is kind of one example of protecting that data, so it can't be changed anywhere, but it can be read anywhere. And that might change to where you don't want it to be read anywhere, or you do want it to be able to change. So, and it gets more complex from that, but this is kind of basics. Then finally, methods. So methods are kind of like your factory line, where you have objects or variables that you send into the function. It does things, and then it spits it back out if it's a function. If it's a sub, then you don't get a return value. And we'll see these in practice. These, if you've done procedural programming, you're familiar with these. I mean, this is what we use all the time. However, with methods, you want it to belong to a specific class and only kind of operate on that class. And once again, these can be private or public based on whether you want things accessible outside the object or not. So let's, with all that theory and talking, let's jump into a case study with the computer fan. So before we do that, Alex, I've just, talked a whole bunch. Are there any questions?
Yeah, so no questions so far. But no, this is very informative, Philip. So I do want to thank you for that. I do want to also note, so you mentioned that this was one of the videos of a series, right, that you've done in the past. Is that correct? Yeah, so I just want to make sure that, again, everyone's aware. So if this is the first video or the first video of the series that you're watching, I highly recommend you go back to our YouTube channel, watch the very first video of the series, just so you can get a general idea of the the path, the flow that Philip has been taking for the series. So again, if you're just coming directly from iLogic, maybe that's the level of expertise that you're coming from, and then going directly into the different classes, the different methods, you might be a little confused, right? So again, just want to recommend look through our YouTube channel, find the series, and we'll probably post a link to that series or a couple of those videos as well. But yeah, no questions so far, Philip.
Yeah, and feel free if things are kind of a little confusing, feel free to slow me down and ask questions. So this is a lot.
Yeah.
But now we get to the point where we're starting to apply it to Inventor, and how we're going to use it with the API. So we're going to focus on computer fan. I made this model up last night to kind of demo some of these different principles on. So the computer fan, we're going to have several different class objects representing the assembly and parts. So pretty simple. The example we're going to go into is fan base and the grate. And then I've left the fan class totally new. I just made it new and left it there. And we'll kind of talk about maybe how we would go about to build that up. So we won't go through and get everything. That would be nice to make this fully working, but hopefully it will help you in kind of seeing an example of how to implement object-oriented programming. So I'm going to exit out of the PowerPoint and head over into the code. So if you have been following along in the series, you'll be familiar with kind of this add-in that we've been working on. For example, the pushing parameters code is all here. And when we talk about procedural programming, you can kind of see that's what we've been doing. We have a button that we click, and it runs, just basically a script. It just runs some code, which works great. However, as we said, the complexity grows, we need to kind of move on from that. So here, I've made another little form, and just a couple little user inputs, and it goes ahead and calls a new class. So you can see there's the making a different object, and we're going to make a new computer fan when we're passing in two variables. So this is our first example of a constructor. So let's jump on inside of it. So here, we're passing two variables in. We'll set private properties up here, private variables, and then you can see that example I gave of having some read-only properties there. Next in the constructor, I'm actually going to try to configure all the different parts here. Some might argue that this could be done in separate functions, that we just initialize the variables and then leave all of these different configures to maybe a configure function. That is perfectly valid. I've chosen to put them inside the constructor here, just so that we have, whenever you make a fan, you're going to also make the classes of your fan base, your grate, and your fan, the specific fan. If we look at the grate here, when we go in and call it, notice that this is a private method. Okay, so I've made a region here of methods that just makes it easier when this class gets bigger that you can hide it. But inside it, I have kind of all the configure methods for configuring the fan base, configuring the grate. Let's go look at the grate example. So once again, you can see I am calling out that private variable. I don't want anyone messing with it, so I left it private. And it's of a custom class I made called Great. Okay. And I'm calling its constructor. So we're kind of having a constructor calling a method, calling a constructor. And in the Great class, this is where I hold everything that the Great part is going to care about. So I have the asset path right here as a private variable. So I can use that whenever I need it. I pass in the box width and the box depth, box width, because I need it for, you know, how the diameter of this thing's going to be, and the box depth for placement issues. So, and there's my constructor. And then I have a method that is a place method. So this will be called later. I don't call it on the constructor. I did that because I wanted to separate it just in case you wanted to make the, you know, the class object before you actually put it in Inventor and save it for later or do whatever you wanted to do with it. And so here we'll see some very familiar code if you watch the push parameters video. So we're going to copy the file, the asset file that we have, to a new file path in a projects folder. We're going to get the assembly document in the component definition. We're going to get the part document and get the parameters and select the specific parameter and push that private variable underscore box width to it. Left some example code here for if I wanted to go do a string parameter. And then we save, close, and ground. You know, place it here with the matrix. I forgot this one the first time I went, and I was like, why isn't it going where it's supposed to? I always remember centimeters, convert to inches. And then we place in ground. So if we want kind of to see this in action, let's open up a new assembly. Oh, hit the right thing here. Let's go new assembly. Go to tools, open up our computer fan thing, and we'll make it so it's kind of weird at first. We'll put it at 8 box width. Now, an asterisk on this, I am not pushing the parameters to the fan base. It's only going to the grate. So you'll see that the grate, if I change it, is too big. So we'll go ahead and hit create. And boom. So let's close this, look at it, and you can see that it's gone ahead and placed that using the instance of a class to make that. Now you can see I haven't rotated it or sized the fan base, but you can kind of see where it's going. So why don't we, I'm going to pause there for a second to see if we have any additional questions.
I'm looking through right now, no questions so far. I'll check YouTube. So yeah, you can continue on. See if
Okay.
there's any questions.
Quiet group today. So now with the amount of code that we just kind of looked at, you might ask, well, why didn't we just do that in a procedural way, just kind of like we did? But if we kind of go back, let's work our way through the code here. So you can see I called place. After I made the computer fan, I called the place method on the computer fan. And it took care of knowing where the project directory was, iterating. So we got a new folder. I can kind of show you the folder structure here. You can see I've been doing tests here, making sure it works. So each time it makes a new folder. This is the last one. It placed our base and grate inside there. So here, because we've, in the constructor, we've created this fan base and fan object of each of the classes there. I can access them now in the place. I know they're there because we did them in the constructor. So this is an example of if you had a separate function that did the configure actions here, you wouldn't be 100% sure that those variables were populated. And so you'd probably want to do some checks to say, hey, is this nothing? Just in case it was called out of order. But because I put it in the new function, I know, unless there's another constructor, because you can have multiple constructors, I know that a new object of this class can exist without those being populated, unless some error has happened. So I'm okay to call dot place on this, and I pass in whatever that place function has. So here is an example of, we talked about inheritance and polymorphism. I'm not doing it here, but if we did have these inheriting from a part class, that part class could have a place function. And we could use polymorphism here to just call dot place, and it would handle that. Now, there are also some things that I could improve here. Remember when we talked about, I believe it was encapsulation, or come up here. We talked about abstraction. Okay, so hiding complexity inside. So here, this is a little bit of complexity we could probably go away with, so that we could just call dot place, not pass anything in, and we'd be good. To do that, maybe we make a global variable that handles this, this project, and then we can, have the base .ipt inside of the actual class. It knows, what it's supposed to be called, and the global knows the project directory. That would probably be a better way of going about this. So there's an example of applying the principles of object-oriented programming as we go. So now that we kind of explored this, why don't we go look at one that has not been made? And Alex, I'll check on time. How are we doing on time?
We're still doing pretty good.
Okay.
Yeah,
cool.
you're doing good on time.
So here we have a blank class. We are calling it here, but we're not doing anything with it. So we have the configure fan function inside the computer fan class that makes a new object. What do we do with it? Well, first off, let's make a constructor. Okay, so we'll go ahead and say public. Oops. Oh, I got to crash this, or it'll yell at me. Don't want to be coding while you're running. Public sub new. There we go. We have a constructor. Okay, it's not doing anything, but we can create our class here. So what might a fan have? What properties? So we might want to, if it had a, I'm just going to kind of make these up as I go. We might have a outer diameter that we have to worry about. So I can come in here and say, we'll set this equal to, if I remember the base, I think that was that. Yeah, I think that's that. And then another thing we might have is number of fan blades. Type num fan blades just to make it really painfully obvious. That will be an integer. I think I start with 5 on this one. Oh, I believe in the example I had, we had 2 different fan types. So we can go fan blade type as string. Now it'd probably be better to make this an enum, but for today, we're just gonna. And one thing you can do is you can use your part as kind of a template. And of course, I crashed Inventor, so I'm gonna have to load up Inventor to do that. So I'll go ahead and bring that up and we'll look at the fan. And you can kind of look at the properties. One way to kind of go about this is build your class with all the properties in it, and then use that as inspiration of kind of what's going to go into your class object. So here we got our fan, and you can see we've got some variables. Let me scroll this up so it's not covering the whole thing. Now I don't have a variable currently affecting the diameter of this because I'm using splines.
Now, Philip.
Yeah.
Real quick, and this is just kind of for me asking here, but you set the, I think, what was it, the fan blade type as a string, and then you said it might be better to do it as an enum. Can you just explain quickly the difference kind of between the two, or why you prefer one over the other?
Yeah, sure. So maybe I'll go into enums here. Let's see, public enum. Let's do a public enum of type, what do we want to call it? Fan type, fan blade type. And then I'll kind of explain what it does. So fan blades, what enums are is they're basically turning a variable that's an integer, but the integer has text kind of tied to it.
Got it.
And so it makes it really simple to put a set of values that something can be, so that you're not using magic strings. Kind of like, for example, here we typed straight, but how do we know, like, I mean, if somebody makes a typo somewhere else in the code, like you have to deal with that.
Got it. So it's just more robust. Like.
Yep. So, and let's say somebody changed the parameter, we'd have to go everywhere we use the string and change the name. That would be painful. However, we could go like this and go straight and curved here. Let's see, there we go. And you can even specifically call out what each of these, because they're glorified integers. So I could do this in a different, manner if I wanted to. But if you leave it blank, they'll default to 0, 1, 2, 3.
Got it.
So that's enums really quick.
Got it.
So
okay, that's perfect.
If we wanted to, now we can go fan blade type as an enum and set this equal to straight. Then when we need it, we can also call .toString, and it will give us this text right there. So you can still use it if you need to pass the text into some object. Okay, good question. So let's jump back here. So here I have my parameter that has, the text value of curved and straight. And when I change it, it goes ahead and runs an iLogic rule that suppresses and unsuppresses some things so that we can have 2 different types of fan blades on one part. And pretty straightforward. If you're interested, I'll pull up the rule. It's just a select case that goes and sets the active setting on each of the features to true or false. Okay. Message boxes for debugging. So while looking at that, you can kind of look through your parameters and say, okay, these are my user parameters that control stuff. I probably need to hold that information for each different object of this fan. Because if I'm going to make, 5 different fans for a computer assembly, each one's going to be different. The fan needs to know all that different information. So here, we're just going to have 3 different private variables up there. I won't worry about the properties because I don't think we're going to access this anywhere else for right now. If we needed to, we can add those in. So as we come in here, why don't we take in a variable? I'm going to call it incoming outer diameter as a double. And then incoming num fan blades, I can type as an integer. And then we'll do fan blade type. As the fan blade type enum. Okay. And then, so we're bringing them in, but it's doing nothing with them. So what we'll want to do, I'm going to cheat here and hold Alt to just grab all of that. And boom, drop those in here. And add a equal. Oh, got one additional line. And then I'll just copy these down. Boop, 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 to just set them to their appropriate values. And there we go. We made a constructor. Okay. So now the other function or method that we had was a place. And we want this to be a public because we want to be able to call it from our computer fan class. So public sub. Now, one note, you can have subs and functions. Functions return a value. So let's say if I wanted this to tell if it worked or not, we could do public function place. Now, for naming your methods, one could name this place fan, but you're going to be calling it on a fan object. So generally, it's better to keep the name of the object you're calling it on off of it. So you can just call like, fan1.place. So here we go. Now this time, I'm not going to pass anything into it. We'll see if we can get away with that. I'd probably have to make some more changes, so we'll maybe skip that. So notice that it's yelling at us. It has this green thing. Because we made it a function, it expects to return something. So I'm going to say as Boolean, meaning we're going to return a Boolean here. And I'll just say return true at the bottom, saying, hey, we made it. Normally, you'd probably have some more logic of like what, if it fails, return false. Okay, so why don't we go grab some of the code. Now, it's yelling at us. Why is it yelling at us? Well, because we said it needed more variables passed into it. So here you can see which variables it needs. So outer diameter, I'm just going to kind of guesstimate here. I think it's minus 0.25. We'll see if that works. And then next one, fan blades. I believe we have a variable. Oh, we're not passing that variable in. So we have, if you remember, combo box, grabbing fan blade number. But we never pass that in to our computer fan. So we can't pass it down through. So there's a couple ways you could go about this, but I'm going to just go ahead and say incoming computer fan, or computer fan, incoming num fan blades here as an integer. And then I can go where it's referenced here. Oh, that's weird. There we go. And now I need to pass that in. And so that's coming from a combo box that I named previously. And we'll go fan blade number dot. I always forget which one it is on combo boxes. I think it's text. Not 100% sure. So if it breaks, we'll know where it broke. So there we pass it in, and then we need to save it. I'll just copy this and say fan blades. I think it's, oh, we never made it a private variable either. Silly us. So we'll say num fan blades. It should be an integer. We want to pass it in. So you can kind of see how, kind of the information gets into these variables. And then once it's in there, you have access to it and you know where it's going to be. A fan knows how many blades it has. Come in here. Now we're getting that passed in and we're all good. So now I got to remember, we were going to do the place, I believe. Come in here. We're in the computer fan. New. Here we go. There we are. And num fan blades. And for right now, we're not going to do that again for sake of time. So I'm just going to pass in a fan blade type here. But normally we go grab it off of the user interface. Enum. Dot. It's giving me an issue here for a second. Oh, did we pass it in as a fan? Oh, I know why, because we made the enum on a specific class. I'll just pass it in as a string right now. And we'll go change that back to a string. You can also make global enums. It's public though, so it should. This is what happens when you try to code on air. So we're gonna go string. We'll pass this, change this back to a string. There we go. So now, yeah, that works. Okay, so I'll pause again. Do we have any questions, Alex?
So we do have a few questions.
Good.
A couple comments here. So Eric is asking, can iLogic use enum? So what we were talking about earlier. Or is that something that we would probably have to look into a little bit more?
Yeah, Alex, have you ever used enums in iLogic? I'm trying to think if there's any enums in there.
Yeah, I personally haven't with iLogic. Again, not to say that you can't do it, but again, we can probably.
Yeah, we'll look into that. My knee-jerk reaction is no. I don't think they have enums built in. It does use VB, so maybe it does. Mm-hmm. I've never used them, Eric, but good question. I'll have to look into it.
Yeah, and then Eric Paul from our team has a comment. So he says one of the other cool things you can do with an enum is use the enum.toString method so that you can still display more human readable information to the user. So I guess just some additional functionality that the enum can provide.
Yeah, you can also override it so that you can make, so let's say you have a set of enums here. So let's go back in to your fan, a straight curve. But let's say you had, for some reason, straight and had a special display name that you wanted to put up on the form that wasn't called straight. You can override it so that you can call, your enum fan blade type dot display name or something like that, and have it put out a different set of strings. So there's a lot of fun things you can do with enums.
Got it. Perfect. And then another comment from Eric here is he's asking if a printout of the code is if it's going to be available.
I'll look into it. It's a little more complex this time because it's in different places, but I think we could probably just get a text, a set of text documents that we might be able to put out. We'll talk about that, Alex. We'll see if we can get that out to you, Eric.
Yeah.
Good question.
Okay. And that's it for now.
Okay. How much time left do we have, Alex?
We have about 10 minutes. So I'm not sure if you're close to wrapping up here.
Yeah, we'll kind of look. So let's look through this fan class and kind of see where we are. I guess we want to do the place function before we leave, kind of to show how we do that. So let's go grab that place function. So here in our computer fan class, it's calling all the different places. So we have a fan base dot place, great dot place. So let's come here and say, we now have our fan. We want to place it. Okay. And like I mentioned before, probably would be better to abstract this information into the class and into a global project directory. But for the time being, because we only have 10 minutes left, I'll go ahead and drop this in here. And this should not be great. This should be fan. And we have the same project directory. And it's yelling at, it's yelling at me because I haven't changed the place function. So now we need to come in and change this. And I'm actually going to go to my great class. It's such a great class. I had to make that joke once. To kind of follow this as a pattern here. So we have our new file path. And I'm going to grab this code and we'll change it a little bit. And this is another example of how object-oriented programming principles should be applied here of I'm copy pasting code. I should start thinking of how I don't have to do that. If I can have an inherited part class that that has this place functionality in it, that all of these child classes off of that part class can access, then this code can live in one place, and that minimizes redundancy, minimizes code cleanup and maintenance. It's what you want to do. So it's yelling at me because I do not have the asset file path here. So it doesn't know what file path is the basis of this thing. So let's go ahead for speed. I'm just going to grab the line here and change it. So here's our asset file path. That should make it feel better about that, but it says great, and we don't want the great. We want the fan.ipt. So that's just the directory where the fan part lies. And then, I'm going to change, here, we can say return false. Remember when we made this a function? So instead of just exiting sub, we could return false and then, use the information that it failed to do something. So let's return false, Okay, I don't think we're importing Inventor. So it's going to yell at me for every time we're trying to use an Inventor object. There we go. Okay, so now we have this straight thing, and we don't want a numeric, so I'm going to get rid of that. And I left that in there for a reason. We're going to go ahead and pass in that text. So we'll go ahead and now if this was an enum, we'd use that .to string. Go ahead and do that there. And we don't want it to be a box width. That doesn't make any sense. So let's rename it. Just right click, rename, and name this fan blade type. That makes sense. And we need to, now this needs to be exact. So once again, if this was an enum, we could use the enum.to string, and that way we don't have many instances of this string getting passed around available to be messed up. Let's go look at this, double check. Yep, fan blade type. Gotta get it exact. And now, where do we want to place this? That is a good question. I think I'm going to put it like a ½ inch over. Normally, you'd have this a little more exact. But I think that's almost right. And so now this could place. Now it's always going to place a straight because that's how we initialized it here, right? So maybe, let's see if we can sneak in getting this from the user before we go. So let's do fan blade type as string. And we'll initialize it to straight just to give us a valid value. Then we need to change our constructor because we need a fan blade type. Fan blade type as string. Hope you guys are really enjoying watching me type. And we'll come over here and put in our combo box, fan blade type dot text. I really hope it's text. And there we go. That should, in theory, pass that into here. Now we need our fan blade type equals incoming fan blade type. And then when we place it, oh wait, let me think about this. So we do that there. Now when we make a new one, we need to pass it in. So we can't just pass that in, we need a fan blade type. So I'm just going to pass it in here. It's going to yell at me because I haven't changed the constructor yet, but we can go do that. Inc fan blade type as string. And oh, it already has it. Oh yeah, because we were passing it in just the blank string. Alex, you're supposed to yell at me there.
I was about to.
Pure programming. Okay, and there we go. So we had it all hooked up with a default, and so when we pass in the actual value, it all handles itself. Okay, so now, I mean, we can run it and see if it works the first time. But while we crank this up, I mean, what are the chances that this works without any debugging? Probably not great. Are there any questions?
Yeah.
So now that, oh, go ahead.
Yep. So we have a few questions here. Some we might have to take offline. One from Jared is he's asking if you can give a quick explanation of what a constructor is and where it should exist in the code.
Okay, so Jared, we kind of went through that earlier. I'm not sure if you came on a little later, but constructor is the method that is used to make an object of that class. So you can see an example of a constructor right there. And when you want to make a object of that type of class, you call the constructor. So it gets it to its kind of default status. So another question, Alex?
Yeah, so there's another question here. We might have to take this one offline again. It's from Eric. So he codes a lot with iParts, where sometimes the size is written as kind of as a fraction, so 2.5 or 2-1, 1.5. And he's asking if there's a way to get Inventor to analyze it and pick the right one. So particularly it happens in nominal diameters where you have 1.5, 1.25, or 2.5 sizes. So yeah, I think we might just have to see an example of this, Eric. So Philip, would you say maybe either sometime today or tomorrow we can reach out to him and possibly get some more information on that?
Yeah, send me an email and we can kind of look into it. I'm not super familiar with iParts, but some members of our team are, so we can look into answering that question for you. Do we have another question?
No, that's going to be it. So the other thing is just we're getting a few comments on people would like to see examples of the code, or if you can send the code that you were using. They said that would be very helpful.
Okay, cool. We'll look into doing that. So here we're going to leave that there. We're going to say we'll put it curved here and go ahead and I don't know. I think a default's curve. We'll go ahead and hit straight, hit create and drum roll, see if it works. So we'll see where it breaks. Oh, whoa, it actually worked first time. Look at that. I mean, I was so confident. Now we didn't place it where it was supposed to be, but yeah, that's easily fixed. So, I mean, there's kind of an example of using object-oriented programming. You can see that as your logic complexity goes up, that it's really useful in being able to compartmentalize all of these kind of variables in an orderly fashion. So we'll switch back over to our little PowerPoint here. So we do these type of things of configurators and tools working in Inventor all the time. So if you are thinking of trying to implement some of this in your work and are interested in picking our brains, or maybe you don't have the manpower or know-how right now to do it, we do mentoring, and also we do projects for our customers. So if you're interested in that, please reach out. Yeah, so if you want to learn more or talk to me, go ahead and give me an email. You can see my email right there, philip.cox@ketiv.com. We do mentoring, and we have we do, like I said, automation projects, and there's kind of the consulting services website, and look out for future AVAs. And if you have ideas of Inventor API future AVAs that would be helpful for you, let us know. So
absolutely, yeah, and thanks again, Philip. Thanks again, Philip, for for taking the time to first of all create this presentation, and then also be very, very elaborate on it. One quick thing that I did want to add. So again, like Philip states here, 30-minute conversation. Eric, I know you're asking some pretty engaging questions. Go ahead and feel free to email Philip. There's his email. We'll go ahead and reach out to you as well, just in case. And then of course, just go through some of the questions that you have that we couldn't answer here. I'm also going to go ahead and paste your first video of the series, Philip. I think it might be this one. It is sometime in September. But this, again, if you're coming from iLogic and this is the first video you watched of the series, it might be a little confusing. So again, to start from the very beginning, there's a link to the first one. It walks you through everything that you need to learn from the very beginning. So with that, I don't see. Let me just double check. I don't see any other questions. Any last thoughts, Philip, before we jump off?
No, thanks everyone for joining, and happy coding.
Awesome. Thank you guys, and we'll see you next week.
Thanks, everyone. Bye.